Good morning. This is B. Naresh, working as assistant professor in AEC department. Today's topic is problems on common source FET amplifier analysis. So, in that, the first problem is in the CS amplifier, as shown in below figure. Let the drain resistance, that is external capital R D resistance, is 5 kilo ohms, and the gate resistance RG is represented as 10 mega ohms, and the amplification factor is 50. And the internal drain resistance, the small RD, is represented as 35 kilo ohms. So based on this, we need to evaluate the voltage gain AV, input impedance ZI, and output impedance, that is represented as Z1. And based on this above problem, they given that a common source field effect transistor amplifier. So why? Because of that, the source terminal is connected to ground potential, and this source terminal is connected as a input side and as well as the output side for a common terminal. And input is measured across the gate terminal, and output is measured across the drain terminal. Based on that, they are specifying that across the drain resistance, external drain resistance, is represented as 5 kilo ohms, and across this gate terminal, the gate resistance is represented as 10 mega ohms. Then internal drain resistance. So when you are observing a small signal model analysis, internally we have the one relation that is represented as mu is equal to gm into small rt, and where gm is a transconductance and the small rd is internal drain resistance, and there the internal drain resistance is represented as 35 kilo ohms. Based on this, we need to calculate the voltage gain as well as input impedance and output impedance for common source field effect transistor amplifier using the small signal model. So for this case, let us consider the given specifications, and we know that the given specifications are capital R D is 5 kilo ohms, means it is also called as load resistance, or we can also use this is external drain resistance. Then this is gate resistance is connected across the gate side, that is 10 mega ohms, and this is internal, or it is also called as AC resistance, AC drain resistance, and the amplification factor is defined as 50. Based on that, we need to calculate the voltage gain. So for this case, let us consider, and we know that generally the voltage gain is defined as it is a ratio of output voltage to the input voltage. And based on this common source field effect transistor amplifier, and based on the small signal model, we know that the voltage gain is represented as minus mu times of capital RD by small rd plus capital R D. Then you can substitute the given specifications value. So minus is a minus, and mu is nothing but 50 into capital RD, that is external drain resistance, is represented as 5 kilo ohms, 5 into 10 power 3 by internal drain, small rd is nothing but internal drain resistance, that is represented as 35 kilo ohms, 35 into 10 power 3 plus, and the capital RD is 5 kilo ohms, so 5 into 10 power 3. Then you can solve this one. It gives that the voltage gain, that is equal to minus 6.25. And here, where this negative sign is indicates that the direction of the output voltage, means the output voltage means V0 is 180 degrees phase shift with respect to the input signal. So it's not a negative magnitude. It indicates that the phase shift, 180 degrees phase shift with respect to the input signal. So hence, we observed that based on the given specifications, the voltage gain is represented as minus 6.25. And again, in that problem, they're asking to calculate or to evaluate the input impedance as well as the output impedance. So first, we are going to calculate the input impedance, that is ZI. So if you observe this configuration in a common source configuration, and when you're drawing the small signal model, we know that it is represented as so it contains ID into GMVGS, and then we have the small RD, and this is the terminal is open, then it is represented as input voltage. So based on this representation, and here external it is connected as a gate resistance, that is a gate resistance is biased with a gate terminal, hence we represent it as R. And under this condition, the input side, input port, we can write ZI directly. It is directly proportional to the given external biasing resistance across the gate side ends. So from this common source FET amplifier and the small signal model analysis, we can observe that input impedance is represented as ZI is represented as RG. So hence, based on the given specifications, they given that the RG value is 10 mega ohms. Hence, so we can write the input impedance that is equal to RG, that is represented as 10 mega ohms. Now similarly, we need to calculate the output impedance. So if you want to calculate the output impedance from the small signal model analysis, then let us consider the JFET small signal model. It is represented as ID into GM VGS, or this is mu into VGS. So this is GM into VGS. Then here the drain current is the flows, and this is a small RD. Let us take this is gate and the terminal VGS voltage, and we are applying the input voltage. Now the drain current is flowing. Then so this is a ID current, hence. So from that we can write ID is equal to GMVGS into 1 by RD times of so we know that mathematical equation ID is equal to GM into VGS plus 1 by RD times of VDS. From this mathematical representation, then we are simplifying this the small signal model of a common source JFET amplifier. Then if you observe the given circuit diagram, externally the load is connected across the drain side. Hence, we are going to connect a external load resistance that is represented as capital RD. From this, now we are going to calculate a Z0, the output impedance. Hence, if you observe this output side, the output network, to determine this output impedance or Z0, from this we know that the Z0 is represented as the parallel combination of the internal drain resistance and external drain resistance. Hence, the Z0 is represented as the parallel combination with the external load or drain resistance along with the internal drain resistance. Hence, from this we can write Z0 is equal to capital RD into small rd by capital RD plus small rd. And we know that based on the given specifications, RD is represented as capital RD is we know that this capital RD is represented as 5 kilo ohms, and the small RD is defined as 35 kilo ohms. Then when the two resistances are unequal and those two resistance are parallel combination, and that gives that parallel combination resistance is approximately equal to a smaller resistance. Hence, when the two unequal resistances are in a parallel combination, that parallel resistance is approximately equal to smaller resistance. Hence, from this representation, we can write Z0 is approximately equal to a smaller resistance value. So from this, the external drain resistance is very, very small compared with the internal drain resistance. Hence, Z0 is approximately equal to external drain resistance. Hence, the Z0 is represented as external resistance. This is 5 kilo ohms. Hence, this is 5000 ohms here. So hence, Z0 is represented as RD is equal to 5000 ohms, or it is also represented as 5 kilo ohms. So to this point, we evaluated the three parameters, that is voltage gain, as well as input impedance and output impedance for a given specifications here. So based on the given specifications, we observe that the voltage gain is minus 6.25, and the ZI that is RA, it is also equal to RG, that is equal to 10 mega ohms, And we also observe the Z naught, that is R naught, that is approximately equal to a capital RD, that is equal to 5 kilo ohms. Now we'll see another problem, the second problem. A FET amplifier in the common source configuration uses a load resistance of 500 kilo ohms. The AC drain resistance of the device is 100 kilo ohms and the trans conductance is 0.8 milliamps per volts or ampere volt inverse. Then calculate the voltage gain of the amplifier. Means that, so this problem uses the common source configuration. Means, so let us take the JFET, and this is the source and the drain, this is the gate. So it uses a common source configuration. Means externally it is connected load resistance. Means, so this common source configuration uses a load resistance of 500 kilos. Means you can write this is RL or capital RD, that is represented as 500 kilo ohms. So it biased with a biasing voltage, that is a VDD. Then in that, means we from these specifications, the external drain resistance, or it is also represented with the load resistance, means they given that 500 kilo ohms. And the AC drain resistance, that is means internal drain resistance, that is represented as a small RD. The small RD is defined as 100 kilo ohms. Then the transconductance, means GM, is represented as 0.8 milliampere per volts. So that is milliamps volt invert here. Then we need to calculate the voltage gain of the amplifier. Now here we need to apply input voltage Vi, and output is measured across the drain terminal with respect to the source. So then first I'll take the given specifications here based on the problem statement. So here we defined as the load resistance, and drain resistance is defined as 500 kilo ohms, and internal drain resistance is given that 100 kilo ohms, and the transconductance is 0.8 milliampere per volts. Now we need to calculate the voltage gain of the amplifier. So we know that again generally the voltage gain is defined as it is a ratio of output voltage to the input voltage. And from the common source amplifier and based on the small signal model analysis, the voltage gain is represented as minus mu times of capital RD by small rd plus capital R. But so here they are not given the amplification factor value. Mu is not defined here. So hence first we need to determine the amplification factor. We need to calculate first the amplification factor. Then we need to substitute this amplification factor in a voltage gain. Then we need to derive the voltage gain of the common source FET amplifier. And capital RD is a known parameter and the small RD is a known parameter. So first the unknown parameter is amplification factor. Hence we need to calculate the amplification factor. And based on the given specifications, we know the some relation between the transconductance and the internal drain resistance. So based on that, the amplification factor is defined as it is a product of transconductance and internal drain resistance. Hence mu is equal to GM into RD. So first we need to calculate this amplification factor. So hence now I am going to calculate this the amplification factor, and based on that the amplification factor is GM is defined as 0.8 milliampere per volt. It must mean 0.8 into 10 to the power of minus 3 into, and the small RD is 100 kilo ohms. Hence this is 100 into 10 power 3. So this 10 power 3 is 10 power minus 3 that get cancelled. Hence the amplification factor is 80. So hence the amplification factor is 80. Now we need to substitute this amplification factor in to observe the voltage gain here. Hence, so based on that, we know that the voltage gain is defined as minus mu times of capital RD by small rd plus capital RD. So now we need to substitute this one, minus to the minus, And now we derive the amplification factor, that is 80. So 80 into capital RD, that is nothing but a load resistance. It also acts as a external drain resistance. And here the external drain resistance is given as 500 kilo ohms, hence 500 into 10 to the power of 3 divided by, and where the small RD indicates that 100 kilo ohms internal drain or AC drain resistance is defined as 100 kilo ohms plus, then capital RD is 500 kilo ohms, 500 into 10 to the power of 3. Then you can solve this ratio. It gives that the voltage gain is minus 66.67. Again, there this negative sign indicates that a 180 degrees phase shift with respect to the input signal, means the output is 180 degrees phase shift with respect to the input signal. So based on the given specifications, we observed that the voltage gain of a common source amplifier based on the following specifications here. The voltage gain is represented as minus 66.67 here for a given common source FET amplifier. Now we'll discuss another problem. In the common source amplifier shown in below figure, let the external drain resistance, or it is also called as the load resistance, is defined as 4 kilo ohms. Now the gate resistance is 50 mega ohms and amplification factor is 40. Then calculate or evaluate the voltage gain, input impedance, and output impedance Z. So based on the given specifications and based on the given diagram, then the source is the common term. If you observe this circuit diagram, the source is the common for input side as well as the output side ends, and the given circuit is acts as a common source JFET amplifier. Based on this given circuit configuration, they are specifying that the load resistance or external drain resistance is defined as 4 kilo ohms, and RG value we considered as 50 mega ohms, and amplification factor, the internal amplification factor, is defined as the 40. Now we need to calculate the voltage gain AV and input impedance ZI and output impedance Z0. So hence first I am going to write the given specifications. RD is the 4 kilo ohms, RG is the 50 mega ohms, and internal AC resistance or internal drain resistance, the value is 40 kilo ohms, and amplification factor is 40. Now first I am going to determine the voltage gain of the common source amplifier. Hence the voltage gain is defined as, it is a ratio of, this is the general definition, it is any gain, it is defined as output parameter to the input parameter. Hence here we are going to calculate the gain parameter in terms of the voltage. Hence it is defined as, it is the ratio of output voltage to the input voltage. Then based on the given specifications as well as the given circuit common source amplifier, now we need to calculate the voltage gain. So at this point the voltage gain is defined as minus mu times of RD by small rd plus capital RD. Now I can substitute the given specifications here. Minus is a minus and the mu is a 40 into the capital RD is 4 kilo ohms, 4 into 10 power 3 divided by small rd is 40 kilo ohms, 40 into 10 power 3 plus capital RD is 4 kilo ohms, means 4 into 10 power 3. Then you can simplify this ratio, then it gives that the voltage gain is minus 3.64. So hence we observe that based on the given specifications, the voltage gain is represented as minus 3.64. Again, this minus indicates that a 180 degrees phase shift between output and input signal here. Now by using this one, based on the given specifications, now we are going to calculate the input impedance parameters. To observe that input impedance parameter, so here I am going to draw the equivalent circuit of the JFET amplifier in a small signal model. So in this common source or in a small signal model of JFET, we know that the drain current is a functioning of a gate to source voltage as well as drain to source biasing voltages, and based on that we represented that id is equal to gm into vgs plus 1 by rd times of vds. Hence, and we are refining the small signal model, and this is a factor is represented as the current source is represented as gm into vgs, and the internal drain resistance that is represented as small rd, and it allows the drain current that is represented as id. Let's take this is the drain terminal and the source terminal. This is the gate, and generally for this JFET, the gate is biased with reverse voltage. So hence there is no current flowing through the gate and between the gate and the source, and it is represented as the biasing voltage between the gate and the source is represented as a VGS, and we are allowing the VI. Now we are going to observe a output voltage V0, and for this case we are placing some external drain resistance or a load resistance that is represented as capital RD. Now based on the given specifications and based on the circuit, the input side a biasing resistance is a bias. A resistance is a bias through the gate terminal that is represented as RG. Hence, if you look about this input side, now we are going to calculate the input impedance of this given circuit that is represented as. So means now we are going to calculate the ZI across the input port. To observe this based on this observation of the given circuit, now the ZI is defined as that is parallel combination with RG ends. So from this representation, we need to calculate that ZI is equal to directly proportional to RG. Hence, we know that based on the given specifications, RG value is 50 mega ohms. Hence, directly the input impedance is represented as ZI is equal to RG is equal to 50 mega ohms. So similarly, we need to calculate the output impedance here. So again, to observe the output impedance, first we need to draw the equivalent circuit, small signal model equivalent circuit. Based on this, again the drain current expression, id is equal to gm into vgs plus 1 by rd into vds. Then if you're drawing this one, so input side is a gate terminal, output side is a drain terminal, then this is a source. Now we are going to apply the input, and based on the drain current expression, we have the two current sources. One current source is represented as gm into vgs, one current source is represented as small rd, then it is represented as drain current id, and externally we place a load resistance that is represented as capital RD. Now at this point, now we are going to calculate the V0, and similarly across this point we are going to calculate the total output impedance Z0, and input side it is a biased with a external resistance that is RG. Hence here we need to calculate the input impedance. So if you observe this output port, now we need to calculate that total output impedance. From that we can say that these two resistances are in a parallel configuration. Hence the Z0 output impedance and the Z0 is represented as the parallel combination with external load resistance and internal drain resistance. Hence it is represented as Z0 is approximately equal to RD is a parallel with internal drain resistance. From that we can write the Z0 is represented as capital RD into small rd by capital RD plus small rd. So at this point, again, let us consider if two resistances means R1 and R2 are unequal, and if it is in a parallel combination, if the two resistances are unequal and in a parallel combination, the equivalent parallel resistance equal to smaller resistance value. And based on this value, the smaller resistance value means capital RD is of 4 kilo ohms and small RD is of 40 kilo ohms. And here the smaller resistance is 4 kilo ohms, hence Z naught from this parallel combination. This Z naught is approximately equal to external load resistance. Hence Z naught is defined as, that is, RT is equal to 4 kilo ohms. So based on this, we observe the three parameters here. So first we determine the AV, the voltage gain. What is the voltage gain we observe? The voltage gain is minus 3.64 we observe. So hence minus 3.64. And ZI, that is equal to RG, that we observe 50 mega ohms. And Z naught, that is equal to capital external load resistance, that is equal to 4 kilo ohms. Now we'll discuss another problem. A FET amplifier in the common source configuration uses a load resistance of 100 kilo ohms. The AC drain resistance of the device is 100 kilo ohms and the transconductance is 0.9 milliampere per volts. Calculate the voltage gain and output impedance of the amplifier. So based on this given specifications, now I'm going to draw the circuit. So it uses the common source amplifier, and here I use the JFET. Let us consider this is the gate terminal, drain, and a source. So common source means source is the common for input side as well as the output side. Let us take this is the input side, Vi. And this common source configuration uses a load resistance of 100 kilo ohms. Hence, a load resistance is placed across the drain side. It is also called as RD. And given that this RL is equal to 100 kilo ohms, it is biased with a biasing voltage, that is a VDD. And then the output is measured across the drain with respect to the source. Hence, this is the V0. And internally it contains a potential difference between the gate and the source, that is represented as a VGS. And again, internally the potential difference between drain and the source, it is represented as a VDS. And they given the small signal model parameters here. So they given that the internal drain resistance or AC resistance, capital small RD, that is equal to 100 kilo ohms. And the transconductance, they given that 0.9 milliampere per volts. So based on these given specifications, we need to calculate the voltage gain as well as the output impedance of the amplifier. So first I'm going to calculate the voltage gain of the common source amplifier with respect to the given specifications. So first let us consider the given specifications. The load resistance is given as 100 kilo ohms and internal drain resistance is given as 100 kilo ohms. And again the transconductance is 0.9 milliamps per volts. So first I'm going to evaluate the voltage gain of the given common source FET amplifier. So generally we know that the voltage gain is defined as, it is a ratio of output voltage to the input voltage. Based on the small signal model and the common source amplifier, for the common source amplifier, the voltage gain is represented as minus mu times of capital RD by small RD plus capital R. If you observe this mathematical relation, here the RD is a known parameter and the small RD is a known parameter. And we know that the external load resistance and internal drain resistance, both the resistances are represented as 100 kilo ohms. One unknown parameter is mu. First, we need to calculate the amplification factor. So hence, first we need to determine this amplification factor. And we know that one relation based on the common source amplifier or a small signal model analysis, we know the some relation mu is equal to Gm times of Rd, where Gm is transconductance and Rd is internal AC drain resistance here. So hence first I'm going to evaluate this amplification factor of the common source FET amplifier. So Gm value is 0.9 milliampere per volts, hence 0.9 into 10 to the power of minus 3, and a small Rd is 100 kilo ohms, 100 into 10 power 3. So this 10 power 3, 10 power minus is a get cancelled, hence mu is equal to 90. So first we observe this amplification factor, mu is equal to 90. Then now I'm going to calculate the voltage gain of the common source FET amplifier. So let us consider the previous analysis, mu is equal to 90. Then I'm recalling this, the voltage gain that is represented as minus mu times of capital RD by small rd plus capital RD. Hence, this minus is a minus and mu is a 90. Capital RD is 100 kilo ohms, 100 into 10 power 3 divided by the internal AC resistance is also 100 kilo ohms, 100 into 10 power 3 plus capital RD is also 100 kilo ohms, 100 into 10 power 3. Then if you simplify this one ratio, it gives that the voltage gain is minus 45. So hence, the voltage gain of the common source amplifier with the given specifications means with a load resistance 100 kilo ohms and internal resistance 100 kilo ohms with the amplification means transconductance or with the amplification factor 90, the voltage gain is minus 40. Again, where this negative sign indicates that a 180 degrees phase shift with respect to the input means the output is 180 degrees phase shift with respect to the input signal. Now again, in the problem, we are going to evaluate the voltage gain of the means the output impedance of the common source FET amplifier. So now we are going to calculate the output impedance for a given specifications. So to determine this output impedance, we need to first redraw the small signal model, and based on the drain current expression, ID is equal to Gm into VGS plus 1 by RD into VDS. If you're drawing the small signal model and we consider that gate is input side, source is output side, and drain is output side, source is the common for input and output. Then we have the two current sources. One is represented as Gm into VGS plus then internal AC resistance is represented as small rd. Then here we are going to place a external load resistance that is capital RD, or it is also called as the load resistance. And here it allows the drain current. Now we need to calculate the total output impedance Z0. And input side we apply the input voltage Vi, and this is gate voltage, gate to source voltage VGS. If you observe this one, from this the Z0 is represented as the parallel combination with load resistance and internal AC resistance. So hence the Z0 is represented as the parallel combination with external load resistance and internal drain resistance or AC resistance. So from this we can write Z0 is equal to RD into small rd by capital RD plus small rd. If you substitute this one, so where capital RD is 100 kilo ohms, 100 into 10 power 3 into again small rd is also 100 kilo ohms, then divided by 100 into 10 power 3 plus 100 into 10 power 3. If you solve this one, the input impedance Z0 is equal to 50 kilo ohms. And we know that if the two resistances are equal, R1 and R2 are equal, and if the both are in parallel combination, and we know that under this condition, the parallel equivalent resistance is equal to exactly the half of the given resistance, either R1 or R2. So that is the reason. So where the internal rate resistance and external load resistance both are represented as 100 kilo ohms. So these two are parallel combination. Hence, the parallel combination gives that half of your external load resistance. And that is the reason the Z0 is represented as 50 kilo ohms. So up to this point, from the given specifications, we observe that the voltage gain as well as the input impedance, output impedance. So thank you. So today's session, we observed that some of the problems on a common source JFET amplifier using the small signal model. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.